Okay, let's dive in. We interact with crude oil products constantly, right? Fuel for cars, plastics, all that stuff. But getting from that thick black crude to usable fuel like gasoline, that's a huge industrial process.
Oh, absolutely. And it's incredibly energy hungry. The way we traditionally refine oil uses just immense amounts of heat.
Right.
And that heat, well, it comes with a pretty significant environmental cost.
Exactly. So the way it works now,
Mhm.
crude oil is like a big soup of different molecules. To separate them, you basically boil the whole thing.
Mm-hmm. Distillation.
Yeah, distillation, collect the bits that boil off at different temperatures.
Mhm.
But it's on this, gigantic scale with massive furnaces.
And all that intense heat means burning tons of fuel, which, translates directly into high energy use and high carbon emissions.
But here's the really cool part.
Mm-hmm.
What if you could skip all that boiling? What if you could separate those molecules just based on their physical size and shape, like using a filter?
That's precisely the idea behind this big breakthrough from MIT engineers.
A totally different approach.
Completely different, shifting from, a heat-based thermal process to physical separation using these special membranes.
And the potential upside, if it scales, seems massive. Our sources are suggesting this new membrane filter could, slash the energy needed for refining.
Dramatically, which would mean a really big drop in carbon emissions, too.
So for this deep dive, our mission is clear. Figure out what makes this membrane tick, how it actually sorts oil molecules, and, well, what it could realistically mean for fuel production down the road.
Yeah, and we've got the actual research details right here from the scientists involved, so we can really get into the weeds.
Okay, let's start with the scale of the current problem. You said refining is energy hungry. Just how hungry are we talking globally?
It's pretty staggering. That process of converting crude oil into fuels using heat fractionation, it consumes about 1%. 1% of all the energy used worldwide.
Wow, 1% of global energy just for that one step.
Just for that, yeah. And because it needs so much heat, which usually comes from burning fossil fuels,
Right.
it ends up accounting for roughly 6% of the entire world's carbon dioxide emissions.
6% CO2 from this one process. You can really see the direct link there between the energy input and the emissions output.
Definitely. So the old way relies on these huge furnaces, these distillation towers, heating the crude oil way up. Different parts boil, turn into gas at different points.
Separating by boiling point. It works, obviously, but it means constantly pouring in energy to make things change state solid to liquid, liquid to gas. Those phase changes.
Exactly. Those phase changes are the energy hogs. You're heating everything, the entire mixture, to really high temperatures. It's just inherently energy intensive.
Okay, problem clear. Massive heat equals massive energy use and emissions.
Hmm.
So now, this MIT potential game changer,
Mm-hmm.
separating by size, how does that fundamentally work?
Well, the core idea is just reimagining the whole separation. Forget boiling points. Think of it more like a molecular sieve, a really, really fine filter.
A sieve for molecules.
Yeah. Zachary Smith, one of the senior researchers on this, he calls it a whole new way of envisioning a separation process. And the key, he says, is making filters that can sort very small molecules at an atomistic length scale.
Atomistic length scale.
Yeah.
So we're literally talking about filtering things down at the level of individual atoms, individual molecules.
Precisely. Filtration at, an incredibly fine resolution. And the potential energy savings are just huge.
How huge?
The projections are that using these membranes instead of heat for crude oil separation could cut the energy needed by about 90%.
90%. For something using 1% of global energy and causing 6% of CO2, okay, those are numbers that make you sit up and listen.
They really are. Though it's probably worth mentioning the idea of using membranes for separating hydrocarbons. It's not totally brand new. People have tried before.
Okay. So if the basic idea has been around, what stopped it? What was the big roadblock?
Right. Well, a lot of the earlier attempts used materials called PIMs. That stands for polymers of intrinsic microporosity. Think of them as sort of early-gen porous plastics. They had holes, which was, the right idea.
Right.
The big headache was swelling. When these PIMs encountered hydrocarbons, they tended to just soak them up and swell.
Like a sponge.
Exactly like a sponge. And when that happens, the pores, the tiny holes doing the filtering, they change shape, or they might even collapse.
So the filter itself gets warped and stops being precise.
Precisely. It loses that size sieving ability. It becomes less of a filter and more just a swollen-up barrier. That was the killer problem.
Okay, makes sense. Preventing that swelling was the nut they had to crack. Where did the MIT team find the inspiration to get around that?
They actually looked at a technology that's already been a massive success story in terms of energy saving.
Yeah.
Reverse osmosis membranes, the kind used to desalinate seawater.
Oh, right. Desalination used to be incredibly energy intensive too, didn't it?
Hugely. But reverse osmosis, really since the 70s, it cut the energy needed for desalination by, again, about 90%. It's a remarkable industrial success. So they thought, maybe we can do something similar for oil.
Okay, inspired by reverse osmosis.
Yeah.
What are those desalination membranes made from?
Usually a material called polyimide. Think of it as a specific type of high-performance plastic, technically MPD-TMC, and crucially how they're made, using a process called interfacial polymerization.
Interfacial polymerization.
Yeah, it's quite clever. You have two different liquids, each containing one part of the final plastic recipe. You bring them together, and the reaction that forms the membrane happens right at the interface where the two liquids meet.
Neat. Okay, so they started with a proven material, family polyimides, and a proven manufacturing trick, interfacial polymerization. How did they tweak it for hydrocarbons, which are obviously very different from saltwater?
They made two really key chemical changes. First, they swapped out the type of chemical bond that links the plastic building blocks together. In the water membranes, it's an amide bond. They changed it to an imine bond.
In amine instead of amide. What difference does that make?
The imine bond is, well, it's more rigid, and it's also more hydrophobic. It doesn't like water. But importantly here, it interacts differently with hydrocarbons. Zachary Smith explains this new polyimine material forms a porous network, and then they add some cross-linking chemistry.
Cross-linking, like adding extra supports.
Kinda, yeah. It
Right.
makes the whole structure stronger. And the result, he says, is something that doesn't swell even when it's sitting in hydrocarbons. That rigidity from the imine bond plus the cross-linking keeps the pore structure stable. It doesn't get distorted.
So the imine bond and cross-linking solve the swelling problem. The filter keeps its shape. Got it.
That was step one. Step two was adding a special kind of molecular building block into the mix. It's called tryptosine.
Tryptosine. Sounds complex. What's special about it?
It's described as shape persistent. Imagine a really rigid, sort of cage-like molecule. It doesn't easily bend or deform.
Right.
By adding tryptosine into the polyimine chains as they form, it helps force the chains to arrange themselves in a way that creates very specific, well-defined pores. Pores that are just the right size and shape for hydrocarbons to pass through selectively.
Ah, so it's like using a specific, rigid Lego brick in the structure to guarantee the gaps you create are the exact size you need for sorting the oil molecules.
That's a pretty good analogy, yeah. So you have the amine bond providing overall rigidity and swell resistance, and the tryptosine acting like a template to engineer the precise pore geometry.
And crucially, this manufacturing method, interfacial polymerization,
Yeah.
that's already used at scale in industry.
Yes, and that's a huge deal for potential scale-up. Tae-Hoon Lee, the lead author on the paper, specifically points this out. Because this method is already common for making water filters, they could potentially just adopt these chemistries into existing scale of manufacturing lines.
That's massive.
Yeah.
You know, a lab discovery is great, but if you can't actually make this stuff efficiently, it stays in the lab. So being able to use existing industrial processes is key.
Absolutely key.
So how did these new membranes actually perform when they tested them?
They did several tests. A key benchmark was filtering a simple mix of two hydrocarbons, toluene and trisopropenzene, or TIPB.
Okay.
In just one pass through the membrane, they managed to increase the concentration of toluene in the filtered liquid to 20 times what it was in the original mixture.
20 times enrichment in one pass. That sounds like very effective separation.
It is, and importantly, they also tested it on a more complex, industrially relevant mixture, something containing components you'd find in naphtha, kerosene, and diesel real refinery stuff.
Yeah.
And the membrane successfully separated the heavier and lighter compounds based purely on their molecular size, just as designed. It showed it could handle the kind of complex mixtures found in actual crude oil fractions.
Okay, so the tech works in the lab, it works on relevant mixtures. How might this actually be implemented in a real refinery? You wouldn't just have one filter, right?
Probably not for high purity. The vision is more like replacing those giant energy-guzzling distillation columns with a cascade of these membrane filters.
A cascade. like passing the oil through multiple stages.
Exactly. The output from one membrane filter feeds into the next, and maybe the next uses a slightly different membrane, optimized for a different size cut, and so on. You use multiple stages to get progressively purer products.
Like using finer and finer sieves in sequence.
That's a good way to think about it. Zachary Smith actually paints this picture. You can imagine that with a membrane like this, you could have an initial stage that replaces a crude oil fractionation column. You could partition heavy and light molecules, and then you could use different membranes in a cascade to purify complex mixtures.
And underpinning all this is the hope that because they use that standard interfacial polymerization technique, actually manufacturing enough membrane material for these industrial cascades should be, well, feasible.
That's the hope, yes. That link back to existing manufacturing infrastructure is a recurring theme and a big plus for this technology's potential.
Okay. And this research we should mention was published very recently in the journal Science. The paper came out May 22nd, 2025, led by Tae-Hoon Lee, with Zachary P. Smith as the senior author.
That's right. And the source material also notes, factually, that the research received funding in part from ExxonMobil via the MIT Energy Initiative.
Right. So let's try and sum up this deep dive. We've looked at what seems like a really fascinating potential fix for a huge industrial energy problem, refining crude oil.
Yeah, this MIT work offers a new path, a membrane filter that sorts oil molecules by size, not by boiling point, potentially sidestepping all that intense heat.
And the keys to making it work this time seem to be those clever chemical tweaks, using the rigidamine bond, adding that shape-persistent tryptosine molecule,
which together stop the membrane swelling and create just the right kind of molecular doorways for hydrocarbons.
and maybe the most exciting part for real-world potential, building it all using a standard industrial method, interfacial polymerization, which opens the door for scaling it up.
It definitely feels like a significant step forward.
So here's something to think about as you go about your day. We talked about oil refining, using 1% of all global energy and causing 6% of global CO2. Now imagine if a technology like this membrane actually delivers that projected 90% energy saving for that single massive process.
Yeah.
If this scales up, what could that truly mean globally for our energy use and for tackling climate change? It's certainly a powerful thought how engineering things at the molecular level could potentially reshape a huge industry.